Welcome to AP Podcast 17.4b, and this is on the Nernst Equation. And this is the equation that we're going to need to find out what is the voltage for a non-standard cell. If you remember our last podcast, we talked about what would happen if the concentrations were not at 1 molar. And so the concentration varies, and we found out that based on whether you have more of one versus the other compound, you could either increase the voltage of the cell or decrease the voltage of the cell. So what we're going to do is look at the Nernst equation and see how it works. And this, again, is for non-standard cells. So there's a nice little derivation in your textbook that kind of gets from Gibbs free energy to this. And then since we've got a constant, and a constant, if you take those three, multiply them, divide them, you get this little equation right here, which is typically what we're going to use. Now this picture that I got has a 2 there, and your textbook has a 1 there. And I do not know if that really makes a difference. I mean, gosh, it's in the 10,000ths place. But anyways, if you see that, don't freak out. If you use the 2 or the 1, I think we'll be okay. And I think I've probably used the 1 in, or I will be using the 1 in this video. So, anyways, the N, of course, is the number of electrons, and we get that by balancing good old Q. Boy, we haven't seen that for a little while, right? That's just the concentrations of the products over the reactants at the very beginning. Okay, so knowing that, let me show you how we would do one of these problems, because they're not too bad. There's a reaction that we've been using quite a bit for these electrochem podcasts, and you can see we've got some aluminum and some manganese, and under standard conditions. So in other words, if I looked at that chart that we've kind of gotten familiar with, I would get a voltage difference of 0.48 volts. That's under standard conditions. But now let's look at the concentrations. We've got 0.5 molar, again, not standard, and aluminum is 0.15 molar, right? So imagine if we were just to think without calculating what would happen to the voltage, knowing that aluminum right here is at 1.50 and manganese is at 0.50, right? If we thought about Le Chatelier, it's going to go like that, right? So we're going to expect this cell to decrease a little bit, right? It's going to be a little less than standard. So let's see what would happen. So using Q, again, I put products over reactants, and I've already got that written out here. And again, notice these are solids, right? So they're not involved in the in calculating Q. So I've got 1.50 for aluminum. We square it, of course, because of the coefficient. And 0.5 for manganese. We cube it because of that coefficient. And we get a value of 18. Now when you balance this out, you've got 3 electrons and 2 electrons. And so the least common multiple of 3 and 2 is 6 electrons. So without showing you both those reactions, because we've already done it in this podcast, this is 6 electrons right here. So when I take the 0.48 and I subtract this value times the log of 18, I get this number right here. And remember a few podcasts ago, or maybe it was the last podcast ago, I said these values are usually small, the change from concentration. So there's proof positive that it is a small change. So we get 0.48 subtracting 0.01, and there's our new voltage. And look at that, it's exactly what we expected. Because of Le Chatelier, we thought this voltage would decrease, and in fact it does. Not by a lot, but it does. So we'll do a few problems like that. Not too bad. This equation right here is, of course, in your equation sheet, and we'll use that quite a bit. Now let's imagine that we have a cell running and we're getting too close to an equilibrium situation. We can involve the equilibrium constant, and that's what this is. So if you could imagine the cell running and running and running, and then we get to the point where we've reached equilibrium. Now if we've reached equilibrium, as you guys know, the products and the reactors are going back and forth and nothing's really happening, right? Well, what do you suppose is happening with the electrons? Well, in the case of the electrons are no longer flowing. So we have, as you can see right here, we have a dead cell, right? The electrons are no longer flowing, and so as far as we're concerned, the battery's dead. It shows a voltage of 0. So if we think about that, if there's no voltage, if there's no electrons flowing, if we're at equilibrium, there is no uh, free energy, to speak. Or I've got it says right here that the same free energy is in both compartments, but we have essentially no free energy. All right. So through the magic of math, I put 0 in that little equation we've used. And then we rearrange for K, and now you can find the equilibrium constant if you take the number of moles of electrons times the voltage at standard state divided by that 0.0591. So it's kind of handy to rearrange that Nernst equation to go ahead and find out the equilibrium constant. So with that, let's practice one. Let's see what we got. Here we go. So we've got a redox reaction up here, and you can see. You know what? Honestly, I don't know what those are. Some kind of thio something. This is thiosulfate, and I'm not sure what you would call that. Sorry for anybody who's listening that knows it, and I don't, but I honestly don't know it. But anyways, let's see what they've got. They've given us the half reactions. That's kind of nice. And the question says balance the redox reaction. Let's save ourselves some time, and let's not. All right. So what would I need here? I would need a 2 over here. Let's see what I've got. -4 plus 3 minus 2. So we're gonna need 2 there and 2 there. And I think then we're charge balance. That's +4. Minus 2 is +2. I've got +6 minus 4. Okay, so there we are. We're charge balance. So I just saved us a little bit of time. You guys can balance redox, no problem. Okay, but let's go ahead and calculate the voltage under standard conditions, right? So we've got 2 reduction potentials here, and at this point in the game, hopefully you can see obviously which one we have to flip, right? And it has to be this one because look at that negative sign. So we would have to make this one Cr2 plus yields Cr3 plus an electron, right? And that would give us a voltage of 0.50 volts, right? And so the E at that point, if we add those two together, is 0.67 volts. Okay, so we've calculated the voltage, and now we've got to find K. Well, let's use that equation that we just looked at, which is the log of K equals the number of moles of electrons times the voltage under standard conditions divided by 0.0591, right? And let's just plug in the numbers. Now, how many electrons are we dealing with? Well, look at this. We've got 2 electrons there and 2 electrons there. So if we were to balance these half reactions, we would multiply everything here by 2, right? And in fact, if you look up there, we did do that. Okay, and so we're going to have 2 electrons, so N equals 2. The voltage is 0.67 volts, 0.591, and when we work that out, we get the log of K equals 22.6. All right. Now I've got to get rid of this log sign, and as you guys know, the opposite of log is that 10x. So when I take 10 to the x and I put 22.6 there, I get a value for K to equal 4.0 times 10 to the 22nd. Holy cow, that's huge, right? But that just tells us this reaction is really favored this way, and that's pretty typical for any kind of redox reaction. So there you go. You can find K by using just a little variant of the Nernst equation, and as long as you can find the number of electrons and you can find the voltage at standard condition, it's really a pretty trivial problem. So like always, if there are any questions, we will talk about it in class. See you next time.